Welcome students. Today in this video lecture we'll be talking about the following topics: beta decay, the beta energy spectrum, the Pauli's neutrino hypothesis, and Fermis theory of beta decay. So this has all to do with the beta decay process and the theory developed by Fermi to discuss the beta decay energy spectrum. So what is this beta decay process? So during our studies on radioactivity, we have studied about this beta decay process in which a radioactive nuclei tries to shed off its excess energy by emitting beta particles, which are nothing but streams of electrons being emitted from the nuclei of radioactive substances. So these beta particles, as they are called, they are negatively charged, of course, because they are electrons. They have ionization capability. They can ionize matter as they pass through it. Also, they have high penetration power. They are affected by electric and magnetic fields. These are some of the properties of beta particles. So, basically, we talk about this beta decay process in which a nucleus it emits an electron. So, this is now when we go into the theory of beta decay process, we know that other kinds of beta decay process are also possible. So this is beta minus decay that we mostly talked about in radioactivity, in which a nucleus it emits an electron. Other way around, under possible beta decay is there. This is called beta minus decay. Another beta decay process is possible, which is called the beta plus decay, in which a nucleus it emits a positron. So this is called the beta plus decay. So what happens? In these both kinds of beta decay process, the mass number it remains the same. That is, the total number of nucleons in the parent nucleus and the daughter nucleus it is same. However, in the case of beta minus decay, the atomic number, that is the number of protons, it increases by 1. In beta plus decay, the number of protons it decreases by 1. So this is the law of radioactive displacement that all of us know. Another kind of beta decay also is sometimes clubbed together with this beta decay process is the what we call the electron capture. It's also known as a beta decay process. We'll talk more about it. It's also called the inverse beta decay, in which an electron is captured by the nucleus. So let's look into this beta decay process. The energy spectrum of the beta particles or the beta decay process, what it basically means is we have different radioactive substances emitting beta particles. So we can measure the energy of the beta particles being emitted by a source by different methods. One way is using the beta ray spectrometer. So basic idea is that we can measure the energy of the beta particles being emitted by a source, and we can plot the number of particles being emitted by the radioactive source or the beta emitter with different energies. So that gives us the spectrum. So if we look into the experimentally observed beta particle spectrum, what is observed is that there is a continuous distribution of energy among the beta particles emitted by a beta emitter or emitted by a beta particle source. So it's not that beta particles are emitted only with certain specific energies. So what is observed is number of beta particles, if we plot along y-axis, and the energy with which they are emitted along x-axis. What is found is that there is a continuous distribution of energies. Beta particles are being emitted with all possible energies from a particular minimum value of energy to a particular maximum value of energy. So this is for the beta minus decay, and this is for the beta plus decay. This is the electrons and these are the positrons. So in both cases we see that there is a continuous distribution of energy. This is the particular maximum value of the energy of the beta spectrum and minimum value. So similarly, if we plot both of them together, we see these are the electrons and these are the positrons, distribution of energy. This invariably there is a continuous distribution of energies, and this side is the number of particles being emitted, number of beta particles being emitted per unit time. This is the intensity. Another important aspect we need to talk about in the beta particle spectrum is the existence of some very high energetic beta particles among the beta particles being emitted by a radioactive source. So what has been found is that these particles are not emitted from the nucleus as such, but these are due to internal conversion. So what is, these are usually, you can see this if we look into the momentum distribution of the beta particles being emitted by a source. What internal conversion means, internal conversion electrons is written here. It means when a nucleus, it emits a beta particle. After the emission of the beta particle or after undergoing the beta decay process, the nucleus can remain in an excited state. So after undergoing the beta decay process, the daughter nucleus that is produced can remain in an excited state. So it can't remain in an excited state forever. So what it does, it comes down to the ground state by emitting or giving off its excess energy in the form of gamma radiations. So these gamma radiations are absorbed by the outer shell electrons. The electrons that are there in the outer shells. So these electrons, in turn, after absorbing the energy from the gamma particles or the gamma rays, they are liberated and they are emitted in the process. So this gives rise to these energetic electrons that are found in the beta particle spectrum. So this is due to internal conversion. So this continuous beta decay spectrum gave rise to some apparent inconsistencies in the beta decay process. Apparent inconsistencies means this gave rise to certain problems as regards to energy and momentum conservation in the beta decay process. So apparently it appeared that some conservation laws were not obeyed in the beta decay process. So let's look into this. There was an apparent non-conservation of energy in the beta decay process. Why so? It's because the parent nucleus, it decays in the beta decay process, it decays into a daughter nucleus along with the emission of the beta particle, that is the electron. So in this process, the energy should be conserved. So rest mass energy of the parent nucleus, considering that the parent nucleus was at rest initially, should be equal to the rest mass energy of the daughter nucleus, the rest mass energy of the electron that is emitted, plus the kinetic energy of the electron. So if energy is conserved in the beta decay process, this should be equal. Rest mass energy of the parent should be equal to the terms in the right hand side. That means for the nucleus, if m1 is the atomic mass of the atom of the emitter, minus the mass of the electrons. So if Z is the atomic number for the nucleus, that is the number of protons, there will be equal number of electrons. So m1 minus Zm, where m is the mass of the electrons, this gives me the rest mass of the nucleus into c square. This is the rest mass energy of the parent nucleus. If m2 is the atomic mass of the daughter that is produced, and in the beta decay process the atomic number increases by 1. So the rest mass of the daughter nucleus will be m2 minus z plus 1 m into c square. This gives me the rest mass energy of the daughter nucleus. And m is the rest mass energy of the electron, so mc square is the rest mass energy of the electron. And let q be the kinetic energy of the electron. So if we look into this balance, cancel out the terms, Zm and Zm will cancel this side, mc and mc will cancel here. So the energy of the electrons should be equal to m1 minus m2c square, where m1 and m2 are the atomic masses of the parent and the daughter atom. So this means what? All the electrons emitted because of this decay should have an energy equal to q. But this creates a problem because only few of the electrons found in the few of the electrons emitted by the beta emitter is found to have this value of energy, and this energy corresponds to the maximum energy in the beta spectrum, the one we are talking about here. Only few electrons are emitted with this maximum value of energy, and if an electron is emitted with lesser energy, the balance of energy, which is equal to q minus the energy of the electron, is missing. Apparently, therefore, there is a non-conservation of energy in the beta decay process. It seemed as if the conservation of energy is not obeyed in a beta decay process. So this was the first apparent inconsistency. Also, so all the particles should have the same energy. That's what I was talking about. Also, there is an apparent non-conservation of angular momentum. Why so? It's because in the beta decay process, the mass number of the nucleus, it does not change. It remains the same. And when we are talking about the spin of nuclei, the nuclear spin, the total angular momentum of a nucleus, it depends upon the total number of protons and neutrons inside the nucleus. So what we found is that if the mass number of two nuclei it is same, then the total angular momentum, that is the nuclear spin, should also remain the same. So it will be either 0 or integral if the mass number is even, or it will be half integral if the mass number is odd. However, in the beta decay process, a nuclei, it converts, parent nucleus, it converts itself into a daughter nucleus by emitting an electron, which is a fermion having half integral spin. So how is it possible that mass number remaining the same, so the nuclear spin of the parent and daughter remains the same, but an electron is emitted with a half integral spin? So there is an apparent non-conservation of angular momentum in the beta decay process. Also, it has been found experimentally that there is an apparent non-conservation of linear momentum. It's found that the electron that is emitted in the beta decay process, it's not found to move in an opposite direction with respect to the daughter nucleus. Or in other words, there is an apparent non-conservation of linear momentum in the beta decay process. So this gave rise to problems in explaining the continuous beta decay spectrum. However, a scientist named Wolfgang Pauli, he came to the rescue. He said that the beta decay process is a physical phenomenon that is occurring, and it can't be special, that it can disobey the conservation laws. He said there is something which people are missing out. Till then, we were scientists were not able to explain why the beta decay process occurs without following the conservation laws. So usually in discussing the beta decay, both the neutrino and the antineutrino are referred to as the neutrino itself. But when we write down the process, the distinction needs to be made. So the beta minus decay here, we are showing a nucleus carbon 14 undergoing beta decay, forming nitrogen 14. And when we write the process, we need to differentiate between the antineutrino and the neutrino. So neutrino is the particle and the antineutrino is the antiparticle. But when we talk in general about the beta decay process, we refer to both of them as the neutrino itself. So in beta minus decay, it is the antineutrino with the electron, and beta plus decay, it is the neutrino with the positron that is being emitted. So the emission of the neutrinos in the beta decay process remove the apparent inconsistencies that were there in the beta decay process. So this hypothesis was given by Pauli in the year 1930. When we do particle physics later, we'll come to know, we'll realize that two other types of neutrinos are there. The electron and the positron, these are called leptons, the light particles. Also we have elementary or fundamental particles called the muon and tau. And these muon neutrino and tau neutrino also are there. Muon neutrino also will have its antineutrino, tau neutrino will also have its antineutrino. So we have electron neutrino and the antineutrino, muon neutrino and the antimuon neutrino, tau neutrino and the anti-tau neutrino. So these are the neutrinos. But in the beta decay process, we talk about the electron neutrino as such. So this is the process what happens in the beta decay. A neutron, it converts itself into a proton plus an electron and the antineutrino. This is the beta minus decay. That is how a nucleus emits an electron. Otherwise, the electrons are not there inside the nucleus. A neutron going into a proton, hence in the beta minus decay, then proton number, that is the atomic number, increases by 1. Other way around, in the beta plus decay, a proton goes into a neutron, converts itself into a neutron with the emission of a positron and a neutrino. So in this process, the beta plus decay, the number of protons, it reduces by 1, and hence the atomic number, it reduces by 1. So now we talk about the Fermis theory of beta decay. So as per your syllabus, we don't need to go into the mathematical deduction of the Fermis theory. So we'll just do a qualitative discussion of the Fermis theory of beta decay. So what is this Fermis theory of beta decay? It's a theory developed by Fermi in 1934 of the beta decay process based on the Pauli's neutrino hypothesis. After Pauli gave his hypothesis, he conjectured that in the beta decay process, apart from the electron, a nucleus emits a neutrino. Fermi, he thought about it and he developed a theory of the beta decay process based on the Pauli's neutrino hypothesis. His theory is based on the following assumptions: that a beta decay process occurs due to conversion of a neutron into a proton and vice versa. Neutron into a proton, that is beta minus decay, proton into a neutron, that is beta plus decay. Neutrino is emitted with a beta particle. So this is Pauli's neutrino hypothesis, and Fermi, he took Pauli's neutrino hypothesis to develop his theory. An important point is, he said that the neutrino and the electron, they don't reside inside the nucleus, but at the moment of decay of the nucleus, these particles are created at the instant of decay. Three types of beta decay he considered: beta minus decay, beta plus decay, and the electron capture, as I told you, also is considered as a beta decay process. He called it the inverse beta decay, or we usually talk about it as the inverse beta decay process, in which a proton, it captures an electron and converts itself into a neutrino with the emission of converts itself into a neutron with the emission of a neutrino. That is also considered to be the inverse beta decay process. So beta minus decay, beta plus decay, and inverse beta decay, or beta zero decay sometimes it's called. Proton capturing an electron, converting itself into a neutron with the emission of a neutrino. So energy is conserved in the process. So the available energy being shared between the electron and the neutrino, obviously. And he considered that the neutrino had zero or negligible mass. So what he did, what his theory is all about, he theoretically calculated the emitted electron momentum range per unit time, or he theoretically calculated the electrons emitted with a particular momentum range per unit time. That is all about his theory. So he considered the beta decay process to be analogous to transition between states, the electromagnetic transitions that occur in atoms. He was inspired by that. In electromagnetic transitions, what happens? An electromagnetic field acts on the system. The system is in an initial state, EI or psi I. This is the energy of the initial state. And because of the electromagnetic interactions or electromagnetic field acting on the system makes a transition from an initial state to a final state. Let me say an atom is in an excited state. It comes down from that excited state to the ground state. Atomic transitions. So those are electromagnetic transitions. So what Fermi he said, he considered the beta decay process to be analogous to transition between electromagnetic states. So he said in the beta decay process also similar phenomenon occurs. The nucleus, there is an initial state of the system which transition takes place to the final state. So initial state, it represents the parent nucleus. In the initial state, we have the parent nucleus, and in the final state, we have the daughter nucleus. Sorry for the typo here. Daughter nucleus, the beta particles, and the neutrinos. So initial state consists of the parent nucleus. The final state consists of the daughter nucleus, the electrons, and the neutrino. He considered the beta decay process to be a transition taking place between these two states. So unlike in the case of atomic transitions, in the beta decay process, the exact kind of interaction was not known. So he called it the electron neutrino field. So Fermi said, because of the effect of an interaction, or because due to the presence of a field which he called the electron neutrino field, a transition occurs in the beta decay process where a system makes a transition from the initial state consisting of the parent nucleus to a final state consisting of the daughter nucleus, the electron, and the neutrino. The transition, it depends on the strength of the coupling between the initial and the final states. So what he did, he developed his theory. It's a quantum mechanical theory. We are not going into the details of deriving the theory, but what he gave was an expression for the transition rate or the transition probability per unit time, which he called the Fermi's golden rule. So Fermi's golden rule gave the expression for the transition rate or the transition probability per unit time. So what it basically means is that when the system makes a transition from the initial state to the final state, beta particle is emitted or a beta decay is taking place. So Fermi's golden rule gave the probability of the transition taking place or the probability of the beta decay taking place. So this transition rate is directly related to the decay probability, of course. And he gave the probability of the electrons being emitted with a particular momentum range. and hence energy range per unit time. So whatever experimentally observed beta spectrum was there that we discussed about in the earlier slides, the number of particles, beta particles being emitted with different energies. So Fermi gave a theoretical deduction for that same probability of the electrons or beta particles being emitted by a source with different energies. So this was the kind of graph that he obtained theoretically without taking Coulomb effect. Coulomb effect means when the beta decay takes place, the electrons or the positrons, they are being emitted by a nucleus. Nucleus, you know, is positively charged. So as soon as the electrons or the positrons are emitted, they are charged particles. So they will be influenced by the Coulomb force exerted on them because of the residual nucleus or the daughter nucleus. So without taking that Coulomb interaction into account, he obtained this graph, this plot. So what happens? The experimentally observed plot was something like this. So what he observed is that without taking Coulomb effect into or the Coulomb interaction into account, the theoretical graph that was obtained matched with the experimentally observed beta spectrum or beta energy curve. For higher energies there was no problem, but at lesser energies what happens? There is a mismatch with the experimentally observed graph. So Fermi, he thought about it and he brought in a correction into his expression, into the equations, by taking into account the Coulomb interaction between the emitted beta particles and the residual nucleus. So when that was taken into account, his theoretical curve exactly matched with the experimental curve. So what you can see here is for lesser energies, what happens? The lesser energies, this is kinetic energy, this lesser energies, the number of electrons, for lesser energies what happens? The electrons when they are being emitted, these are negatively charged, so the nucleus which is positively charged will attract them. So what will happen? Their kinetic energies will be slowed down, the kinetic energies will be lessened. So there is more probability of lesser energy electrons being emitted, more number of lesser energy electrons being emitted. The energy of the electrons because of the Coulomb interaction they are slowed down. Other way around, for the positrons what happens? As they are emitted, the Coulomb interaction, the residual nucleus, it repels them. So the number of electrons being emitted for lesser energies is higher than the number of positrons being emitted. But for higher, very high energies, what happens? The electrons and the positrons, as soon as they are emitted, they fly away from the nucleus with very high energies, and hence the Coulomb effect is not seen. But for lesser energies, the electrons and the positrons is separate out. So that's all about the Fermi's theory of beta decay, the Pauli's neutrino hypothesis, and the beta decay process as such in general. So thanks for your listening.